He had worked 20 years as an engineering project officer at the Naval Sea and Space Warfare Systems Commands. He also worked 30 years for Raytheon Company, spent 10 years in the manufacture and repair of naval nuclear reactors and submarine propulsion systems.
Are those three subjects, climate, energy, and environment, and they're intertwined. So they interact with each other. Energy is the lifeblood of civilization, modern civilization. We can't survive when it stops. I'm going to talk about the problem, trying to join the three of these things together and make sense out of them. What can be used to solve the problem once we define it, and then what the people are, who the people are that could actually solve it. And it's usually not engineers, it's usually the politicians who spend our money. So think about that. I'm going to talk about energy machines of all types, as Jan said. I'm going to cover them all. And this is an energy machine. Does anybody know where those things are going right now? Yeah, have you seen them offshore?
Yes.
Sure.
Okay, well, they're that big.
But
They're 3 times higher than the deck of the Newport Bridge. And you don't realize that until you actually see them up close. They're not the size of the one you see out here in Portsmouth, right around the corner. So I'm going to talk about climate a little bit first. The press has led us to believe that scientists all agree that man is the control knob for climate. That's wrong. We can burn all the CO2 we want, we can dial it up or down, but that's a very small amount of what controls climate. What actually controls climate is nature, and that has gone on for millions of years. So we're going to take a look at climate history by looking back. This slide out of the Washington Post shows the Earth's climate going back 500 million years. It shows we are at the lowest Earth temperatures of that whole period. Now, we weren't around even 1 million years, but this is 485 million years. And this red line on the bottom, and we're here right at the end of the red line, we're at the lowest average surface temperatures ever. So when you hear that the temperature of the Earth is warmer than it hasn't, that it is, that's cherry picking. You're not looking back far enough. You look back through history, we're at the lowest surface temperature ever. Those surface temperatures have ranged from this red line up to this green line. That's a 40-degree variation. Now, we weren't living through most of this time. The dinosaurs ended right here when a large spike of temperature rise was caused by a meteor hitting the Earth. The largest mass extinction of living things ever happened back here at around 250 million years ago, and that was due to volcanoes. So now we're going to look at, and by the way, these triangles, this one, this one, this one, this one, these are large glacier periods. Now we're going to look at our current time period, and that's called the Holocene. And it covers 12,000 years ago to the present. So this is the present over here. This is 12,000 years ago. And this black line coming up like here is temperature coming up, rising after the last ice age. Now, the last ice age took place 19,000 years ago. The temperature rose, and then 10,000 years ago, and right in here, 8,000 to 4,000, right across here, it hovered kind of easily in one spot. But this was the period of time, 8 to 4,000 years ago, where humans flourished. And we called this a climate optimum. Climate scientists call this a climate optimum because this is where humans in the area surrounded by the Nile, the Tigris, and Euphrates actually multiplied for the first time, grew pretty quickly, up to maybe 1 million people. And you'll notice that this line right here is a dotted line and it says it's 0. That 0 is really the temperature, the average temperature of the Earth at the time of the Industrial Revolution, around 1800. So they show it as 0, the climate people now who are having you worry all about climate, because when you show it on that scale and you go up to 1.5 degrees centigrade up here, there are a lot of people saying we're going to have really bad problems if we go up that high. What is unknown right now to most people is that we've already gone up 1.3 of that 1.5 since the Industrial Revolution. So we only have a couple of tenths of a degree centigrade more to go up before the world ends, if you will. Well, that isn't really going to happen. This is the hockey stick issue of, you'll see on the press, oh, look at this, the temperature's rising so fast and so high. It's rising a half a degree from now, if even that. What the scientists were worried about 40 years ago was this. This is the glacier that covered half of North America 19,000 years ago. Scientists were actually worried 40 years ago in the 60s and 70s, not about warming, but going into another period of an ice age. And they published a lot of journals. They were all over the scientific and university areas, but nobody read them, so they returned to the press. Here's a Newsweek article. And what they were worried about was this trend here, from 4,000 years ago down to now. This is now. You'll see the average temperature from these models. These are all models in color, by the way. And you can see that they vary all over the place, so it's really kind of interesting that you have one model way up here, the other model way down here. But anyways, the average was going down, and the scientists were really worried about this dip right in here. That's the Little Ice Age. That took place in 1400 to 1800, 400 years of really kind of cold temperatures. So the Thames River was frozen for 400 years. Sconnet River was frozen. Narragansett Bay was frozen. A lot of people died from cold. And right here where we are now, the scientists in that period of time said, we got to stop it. We're going into another one, so there'll be another dip coming down. This is what the scientists were saying at the universities and at NASA. So here's the article from Newsweek, right here, science article. They give it a full page. I'll just quote the last paragraph. Climatologists are pessimistic that political leaders will take any action to compensate for the climate change. And they're talking about a glacier now. They're talking about freezing, not about warming. This is 40 years ago. And here's what they proposed down here. They said, we're going to have to take measures like dumping gasoline and oil all over the Arctic and lighting it on fire to create soot, which will cause the sun to absorb more into the ice and melt it. This was actually what was going on 40 years ago by the same kinds of scientists, not the same ones, but the same kind. And I think I brought some copies of this if anybody wants to read it. Okay, I'm not worried about temperature. I'm not worried about a half a degree temperature rise, because at the most, if we go even that much further than we are now, we're going to see more greening of the earth and less deaths by the cold, because cold causes way more deaths than summer heat, so-called heat waves. I am worried about ocean rising, and I'm worried about how fast it's going to happen, because the models for ocean rising are all over the place. The IPCC, the International Panel on Climate Change, predicts sea rise of 9 to 24 inches by 2100. That's a pretty big range. Now the ocean is rising because as I showed you, we're at the end of an ice age. We're in a natural melt period. So the glaciers are melting. And years ago, you could walk to Martha's Vineyard. It was connected to the mainland. But since 1880, 11 inches of rise has really happened at Battery Park, where we really have a gauge. They stuck a gauge from 1880 there, just a pipe, just a stick in the water, and we know that we've risen 11 inches since then. Now the IPCC models predict this large range, not 11 inches, but maybe 24. Do we need an energy policy? That's the question I ask as an engineer. If it really happens that the ocean rises 2 feet by the end of the century, I think we need a lot of energy just to build dams and dikes around cities like Manhattan and Providence, like the Dutch have done, and reclaim the land, or move inland. This is nature, this is not man that's causing this. Humans have harnessed energy over our whole existence. So humans, or upright apes, if you will, back here, 300,000 years ago, discovered fire and started using wood and dung to stay warm and to cook. And we continued using wood, dung, then peat, and then wood, dung, and coal, oil, and gas at the start of the Industrial Revolution, after World War II, after World War I, especially as we took over the oil fields in the Middle East. So we've been using all this stuff forever. And the population, this red line, stayed rather small until we went to coal, oil, and gas, and then the population shot up from less than 1 billion to almost 8 billion now. We're using all these things: wood, dung, coal, oil, gas, hydro, and nuclear now. But we haven't retired wood and dung. Half of the world has little or no electricity. So they're using wood and dung still. We're talking 4 billion people. You don't hear that in the mainstream press very often. So the future is, what's going to happen here? These are the so-called green energies. These are the energies, the types of energy that don't give off carbon dioxide. And that's kind of the definition of green. We'll get into that in a moment. So nuclear, solar, wind, and batteries give off no carbon dioxide when they're operating. Before I get into the energy pie, which I'm going to show you how energy is used, I want to stop and take a look at what's going on in China. We'll start with the Olympics in 2022, the Winter Olympics. You may remember them on TV. COVID was going on too. The Chinese party closed down 10 or 12 big coal plants around Beijing well in advance of the Olympics in order to not have this scene on the streets in Beijing. Smog. And the interesting thing is it worked, but the interesting part was that at that same time, 2022, China was building 2 large coal plants a week, and they still are. They have not stopped. In fact, they're building 3 if you consider the fact that they're building them in Indonesia and Africa. But also in 2022, China was planning and is now building 150 nuclear reactors in the next 15 years, more than the rest of the world has built in the last 35, according to Bloomberg. This is the long-range plan in China. It is to go all nuclear. You won't hear that. You'd have to read the Communist Party manifesto to figure it out, but that's the plan. Bloomberg knows it too when you look into it, do your homework. So now let's slice this energy pie. So roughly, these three slices of the pie, industry, transportation, and electricity, roughly make up 1/3 each of the world's primary energy use. Now, primary energies are coal, oil, and gas, nuclear, and what we call flow energies. Flow energies are not fuels, they're flowing material. So are flowing atoms. Think hydro, flowing water, solar, flowing photons from the sun, and wind, flowing. Batteries are storage medium necessary, conceptually at least, for solar and wind to function, because you can't rely on intermittent solar or intermittent wind to run an electric grid. It would fail immediately. So the big proposal right now is batteries. Well, let's look at the energy pie. Let's start with renewables. Look at this astounding growth in renewables from 1965 to now. Now, isn't that great? People, this is the kind of chart you'll see in the paper. You'll see it at Sierra and Greenpeace. We're going gangbusters. We're going to be all renewables in no time at all. So from 1965 to now, the growth in renewables, the biggest one was right here, this blue. That's hydro. And so it occupies right now half of the renewables in the world. The other stuff that started around 2000 right here is wind right in here. Look at that great increase, and solar right here, a little smaller wedge. So wind and solar are about 1/3 of today's renewable electricity, because this is only feeding the electric grid, not transportation, not industry. And up here, biomass, wood pellets. So we're on this wonderful growth path where renewables is going to take over the world. And the cherries here mean something. It's called cherry picking, because this is what's really happened. That little chart that I just showed you is right up here. If I were to stack that on what we really use right now around the world, including coal, oil, and gas, the renewables are invisible. You can't even see them on this chart. So solar and wind is right in here. So we're going to power the world, so the current administration says, with solar and wind, and it's going to, first of all, take over the whole electric sectors. We're going to have everything electric by, everything that runs on electricity is going to come from solar and wind. Well, right now, the amount of solar and wind that are in the electric pie is this green line. It hardly exists. So how in the world are we going to get solar and wind to power all of electricity, all of transportation, which would mean electric cars, and industry, which requires a lot of electricity to melt steel? It's impossible. There's no way that's going to happen. To look at it just now, so now would be just this side right here, 2025, 2025. Look at that right now, and this is what it looks like. Coal, oil, and gas from here to here are 84% of the world's primary energy use. Nuclear is here at about 4%. Hydropower is here at about 6%. And that small amount of solar and wind that I showed over here, that's 2.2% of the world's energy use and 1.1% for solar of the world's energy use. Solar and wind can't even keep up with the additions every year of more coal, oil, and gas, especially when we look at China, which I talked about before. Next, I'm going to, you might not believe me, you're standing there and saying, well, this guy's a nuclear engineer, he's going to talk about nuclear reactors, and where is he getting all this information? And what does the government say? Well, here's what John Kerry says. And he says this because for 15 years, he's been our ambassador, our climate ambassador. And he goes to all these conferences in his private jet and says things. John Kerry said at the conference of the UN in Paris in 2021, the USA has increased wind power 300% and solar 3,000%. That's the astounding renewables cherry picking. Yet he unabashedly states this truth, quote, if all the industrial nations went down to zero emissions, it wouldn't be enough. Not when more than 65% of the world's carbon pollution comes from the developing world. Now, that was probably the most truthful thing he's ever said as the climate czar. Half the world lives with little or no access to electricity. That's right out of Forbes' article. You can read it this week. And you can see the pie here. This is the pie in 2004. This is the whole energy pie of the world.
This is the growth of the world energy consumption pie from 2004 to 2023, a total of 175 very large ecojoule units. That is a pie growth of 39%. The blue slice is solar and wind. It grew from nothing to 37 units in the same period of time. It has not come close to keeping up with the growth of energy use in the world, period. This wind and solar blue slice of 37 energy units can't even keep up with the incremental energy pie growth of 175 units. There has been no energy transition in 20 years. There has only been the minuscule addition of wind and solar energy consumed with an immense infrastructure cost in the trillions of dollars.
So Washington mandates that the green energy has to be something that we're going to use. And the states just sort of say, oh yeah, we need to use solar and wind. We need to follow the law. So let's define green energy. So from an engineering point of view, I'm going to talk about green energy. So energy machines, right? The things that I showed you, like the wind turbine, and I'm going to show you all in a minute. In order to be green, they need to operate without giving off any emissions, any CO2 especially, right? So wind, solar, batteries, and nuclear, they fill that bill. You can say they're all green at this point in time. The next requirement is that machines made, these energy machines have to be made with carbon-free fuel, carbon-free energy. That means that you can't use coal, oil, or gas to build the wind turbines or the solar panels. And guess what? we're not using renewable electricity to build anything. And we're using coal, oil, and gas. Most of it is coming from China. 90% of the wind turbine materials and the solar panels come from China. In the short, wind, solar, and batteries are out when we're going to define green. And when you're using a system of energy, you cannot have gaps in it. And if you did have gaps, you can't fill them up with fossil fuels or batteries. So wind, solar, and batteries are out. You can't have gaps. You have to have continuous energy. Continuous, survivable, weather survivable. Solar and wind are not survivable in severe weather. They're certainly not continuous because they're intermittent. You have to have energy that's dispatchable. You have to have somebody in a control room that flips a switch and sends energy from here to Virginia because Virginia just had a tornado or a deep freeze, and solar and wind can't do that. Neither can batteries. The most important word in here, though, is density. The energy that we need has to be the best available, cheapest, dense energy that we can find on Earth. And currently, that's coal, oil, gas, and nuclear. Wind, solar, and batteries are out. The optimum dense energy has to be good enough or powerful enough to run continuously and power everything, while at the same time, because of the government mandate that we have to get rid of CO2, you have to remove the CO2 while you're powering everything. So of course, wind, solar, and batteries are out. They're insignificant. So what I suppose we could do for policy is this. We could go all nuclear and satisfy all requirements, but that's certainly not going to happen in the United States. It is going to happen in China. And it won't happen in the United States until we change regulation and do some education on radiation. We could go to all natural gas today. If we went to all natural gas today, we would cut our emissions in half for the same amount of electricity, and all this problem would go away. You wouldn't see any more talk about climate. So a new federal energy policy might be something like this. Now, I'm a member of the Energy Council of Rhode Island, and we've formed an organization to do this teaching. Much of what's in here is from that group. And this is what we're advocating, CNN, which means go from coal, which we still have a lot of in this country and around the world, 80% almost, coal, oil, and gas. Go to gas next. So we're switching this country, if you want a federal energy policy, from coal to natural gas. That cuts your emissions in half and all the problems go away. And then in 2 decades, do what China's doing, go completely nuclear. So let's talk about the energy machines that might be able to do that. I'll end with nuclear. So energy machines have externalities. These are side effects. They're either good or bad. They're usually not taken into account up front when we build something. This is the solar energy externality. This is a map showing the baseball and golf ball size hail that hits the country every year. It happens frequently. You don't see this in the mainstream press. This is what solar farms look like after a hailstorm. And what happens to those solar panels? This is what happens, because China no longer will take them back. China was taking them back, but they're toxic. And they've been burying them in their landfills, and they've polluted a few rivers. So you can't bury them. They're not recyclable. You'd have to use more energy than they've ever made to recycle them. So this is where they end up. They end up in the backyards. Now this isn't a hailstorm here. I lived in Florida for 10 years. This is a few years back, we had a Hurricane Ian, I-A-N. It wiped out Fort Myers. These are the solar panels off of the roofs in Fort Myers, Florida. There weren't any left. The whole city died and flooded, and a lot of people died. So you go inland to Florida and you still find these things here, sitting on the land trying to figure out what to do with them. That's waste that we can't recycle. The other, the next, so I just looked at solar. Now we're going to look at wind. The big thing with wind are the blades with respect to ecological significance, because over a year, approximately 60,000, 64,000 when you add these two together, blades are replaced. These number, 3,800, are from failures. This is historical, looking at land wind turbines mostly. The repowering blades are because the blades normally don't last any more than 10 years. Now, why is that? It's because they get eroded, and they go very fast at their tips. They erode, and it's hard to repair them and maintain them. You'd have to have men like ants crawling all over them and refinishing them, which is done. It happened at Block Island. I'll show you a picture in a minute. So with 64,000 blades every year, what's going to happen? This is going to happen. Backyard in Texas. This is the biggest Caterpillar tractor that exists. These are maybe 100 to 150 foot long blades cut apart, and this is a landfill. You won't see this on the mainstream press. The other externality for wind machines are these red lines, also known as hurricanes. Maybe you've heard of them. These things wreak havoc on wind turbines and solar farms. And if we have the largest wind turbines ever off the coast, you can expect to see a lot of them falling apart. Here's Block Island. Block Island wind has 5 turbines, the wind farm. In 2 years, this is what had to be done because the blades eroded at their tips, being hit by sleet and birds. And these guys are little ants, and they are hanging from cables. It's not the kind of job that the unions really want to do here, but they're hanging from cables and they're resurfacing the blade and epoxies and smoothing. And that happened on all the Block Island wind turbines. This one you probably have heard about because it has been in the papers. This is Vineyard Wind, July of 2024. And this may look like the Block Island turbine. It's not. The men on here, if they were crawling around on this blade, you wouldn't even see them. They really would be ants because this is the size of the turbine that I showed you next to the Newport Bridge. So when this happened, 100,000 pounds of materials fell into the ocean, fiberglass, foams, plastic, and has been a real problem. Now, if you want to see the environmental effects of this, and if you want to talk about what this is doing to animals and other creatures in the ocean, I recommend that when you leave, you take up some material here from Green Oceans, because they've done the homework, involved in big lawsuits to try to stop this silliness from going on, and the facts are in here, all very well referenced, and you'll learn about the effects on the environment, including fisheries and whales. Here's the effect on the environment from the Vineyard Wind. Turbine failure. So these shards and this foam are still washing up on the beaches from Cape Cod to Long Island. Some has washed up here. I think this is Horseneck area. I may be wrong. There are some people here in the audience that can correct me, but Horseneck Beach area. These things, these are relatively big pieces, relatively big here. They're even bigger. You can see some over here. But imagine the small parts of the plastics here that are still in the sand and will be there forever. So Martha's Vineyard right now is kind of rethinking the fact that they took a lot of money to support wind turbines. Okay, let's look at the last of the 4 renewables. So we had solar, or the 3, solar, wind, and batteries. This is the state of battery technology. This is a lithium-ion battery here, next to the matchbook. There are 60 of these in a bike, in my bike, an electric vehicle bike. There are 7,000 of these in a Tesla car, like. There are 19,000 in a Powerwall, if you should be inclined to buy one and put on your garage wall to help out the environment. There are 19 million of these in an industrial solar or wind plant termination point on land, such as Quonset Point or Somerset. And those 19 million are in a big box the size of 3 football fields. This technology is woefully inept to store energy, because that's it. Imagine soldering 19 million of these together in packages and putting them in a box, it's asking for a disaster, because any of the soldering breaks, you got a fire. So it's dangerous at all levels, but wind and solar cannot exist in an all renewables economy without the battery farms. So you're going to see your tax dollars on your electric bill and it on your electric bill going into this technology, which does this. These batteries only store 3 hours of energy, then they have to be recharged. So from what? If you're going to recharge the battery with a solar farm, forget it. It isn't going to recharge it in a week. They're extremely expensive. They have a very short lifespan, and they're terrible for the environment. So here's a small solar farm with a battery adjacent to it. The battery catches on fire. It can't be put out with water. It burns until the whole thing melts down. The fumes are very toxic. You have to evacuate your city. That's actually happened in many places. You don't see it in the mainstream press. This is the what's the name of the company? Rivian, I think, the second largest maker of electric vehicles in the United States after Tesla. This is their parking lot about a year ago, less than a year ago, where these cars were all stored outside. One of them spontaneously burst into flames, and the heat, because it's so high, from that one car lit off the whole parking lot. And so they lost a few months of production of their cars. The good news is, for Rivian, is that the Biden administration just gave them $2 billion from the ironically noted Inflation Reduction Act, and you're paying for that. This is a typical car fire. It happens in many car garages all over the place. A lot of this happened in the hurricanes that went through North Carolina, by the way, just from the water. But this one just burst into flames and caused the cars next to it to be damaged. This is probably a gasoline car, but it caught fire. This is in Connecticut, where I used to live, and all the politicians got out and said, look, we've got 5 new completely electrically powered school buses. On the first day, this is what the school bus looked like.
Oh.
But luckily, nobody was killed. Now this one I really like, because the firemen got there very quickly. Their fire garage, all the fire engines are on fire. Now why is that? Why do you think that is? Well, it's because the Biden administration gave them a loan to buy an electric-powered emergency response vehicle. The fire department doesn't exist anymore. That is a problem. Batteries are not safe. This is a bike shop here, and the night camera caught the battery right here going off. You can see it's like a blowtorch. Completely burned the place down in no time at all. I can also say that there are folks here. Gail, raise your hand if you're here. So Gail's here from Bike Newport. I support Bike Newport a lot. She gives a course on bike safety. Part of it includes how to maintain your lithium battery in your garage. You probably don't want to charge your lithium battery right now in your garage, because cold temperature can result in what's going on right here. The last one I want to look at of the 4 greens, so solar, wind, batteries, is nuclear, and it has externalities. Up until the Chernobyl thing happened, all the externalities have been identified up front for every nation except the USSR during the Cold War. So this is Chernobyl, north of Kyiv in 1986, and this is the meltdown. The other externality, and I'll talk more about this in a moment, the other externality is waste. This is a nuclear power plant. The plant's actually over here. This is a cooling tower from the nuclear power plant. That's just water vapor coming up here, so as not to use the water from, say, Narragansett Bay and return warm water to the bay. So that's a cooling tower. It's used in all kinds of coal, oil, gas, and nuclear. This is the waste right here. These caskets, here they are in the factory, made of a foot-thick steel. They house the waste of the nuclear power plant. Now that waste has accumulated over 60 years, and that's all of it right there. By the time it gets out to the lot where the waste is actually stored, It's harmless. It's about twice background, and background is harmless. So background radiation, I won't use the numbers. So you're about twice background. So you can sit here, you can have a picnic, you could hug these things, and they are designed to take a 747 crashing into it. They'll move around, but they're not supposed to be taken apart. The good news is that today's reactors, the ones that I've been working on for 10 years, can burn all that waste. We don't have to bury it. It's very valuable and can power the country for probably 50 years, just the waste that's out there. And I'll show you the pictures of those reactors in a moment. Now let's go back to Chernobyl. What happened at Chernobyl in 1986 was a true meltdown of a reactor right there that did not have a container around it. What it did have around it were walls made out of carbon coal. Actually, the graphite that's used in the walls has something to do with moderating the nuclear reaction. But when it melted down, the coal, of course, caught on fire and it literally had the whole place fall down. There are 3 other reactors next to it that are still that we're still running for another 10 years. I'll talk about that in a moment. These people right here are firemen from the neighborhood Pripyat, right, the city of Pripyat, which was built next to the plant. They were called in an emergency to go put out a fire. They were not told they were going into a highly radioactive area. They all died. There were 52 of them, and then the jig was up and Russia had to say, oh yeah, it's not a fire, it's a nuclear meltdown. That took a week for Russia to admit that. And then the World Health Organization and the Atomic Energy Commission all got mad at them and said, you can't be sending people in there like that. So Russia said, okay, we'll do with what you recommend. What do you recommend? Well, here's what was recommended and what was done. Send in more people, but only have them stay in there for a very small amount of time, and so they don't get a lethal dosage. Kind of like taking a cancer treatment. You go in a few times, you don't get a lethal dosage. Cancer treatments are very, very intense radiation. Well, how many people do you think went in? It begins with a 6, and it's not 60, it's not 600, it's not 6,000, it's not even 60,000. It's 600,000 people in the next 10 years went in for a short amount of time to take care of this meltdown. Now, in the first few months, they only stayed in for 5 minutes each. In the next years, they might have stayed in, well, gradually going up, to be able to stay in for a day. But it's 600,000 different people. They've all been studied since 1986 to see if they have any cancers. Well, what do you think? Oh, if you watch the news, you'll think, oh, it's still estimated that 10,000 people are going to die. Well, statistically, from 1986 till now, and they've all been studied by many organizations, 0 have died. 600,000 people entered this highly radioactive area to begin with, and none of them died. There were deaths from the release of radiation in the area where children were drinking milk, and the milk had absorbed radioactive iodine that got into the children's thyroid glands, and maybe another 50 have died from thyroid cancer. Several thousand were treated for thyroid cancer and are still alive. Ironically, they were treated with radiation treatment to kill the cancer. So it depends on your dose rate and how much you're getting at any one time. Radiation is really interesting. What we also find is that people that get large amounts of radiation, larger than background, like 100 times larger, their disease profile is less than the rest of the population. That is a very interesting thing to look into, and I don't have time to go into it here, but that is true. The radiation at certain dosages immunizes your body, makes your immune system stronger to all kinds of disease. Okay, I mentioned density before. I said it was very important. Let's quickly go through this and see what I'm talking about. So we can go to energy density by weight, and we can see that this egg of uranium, egg-sized uranium, if we were to use that for your energy needs for your whole lifetime, that includes everything, transportation, cooking, heating, everything, all the products that you use that were made with coal, oil, and gas, for example, if we made them all with, if we don't have nuclear and we use coal, oil, and gas, we have 21 elephants of coal, oil, and gas. That's, I can't read it, 88 tons of coal per person here in the room. And what that means is that the 88 tons of coal is in the red here. That's 88 tons of coal. Interestingly, chemistry, the amount of carbon dioxide given off by 88 tons of coal is 3 times the weight of the coal. So 270 tons of gas are released in the atmosphere. That's what the climate scientists say is causing man-made global warming. So that's coal, 3 times its weight. So 21 elephants of coal, puts out 60 elephants worth of gas into the atmosphere, carbon dioxide. This right here is oil. Oil puts out a little bit less. It's better than coal. Here's your carbon dioxide. Here's gas, and this is why I said we could switch from coal to gas immediately and put out half of the carbon dioxide. There's the carbon dioxide for coal, there it is for gas. That would solve the climate problem immediately. Or we could go in the long term, like China's doing, to nuclear, and down here you hardly see any carbon dioxide. This chart includes a little bit because the plant was made using coal, oil, and gas to make the steel and cement. But if you went all nuclear, you would never see any carbon dioxide again. If you had enough nuclear power reactors to make more, you could do it. You can never do that with wind or solar. Now let's look at energy density by area. So this is Boston, right here where the green dot is. If we wanted to have Boston completely run on renewables, solar and wind, or biomass, we would do the following. We'd put solar panels everywhere, on every rooftop, and every lot that sees sun, and it would occupy this ring around Boston. That's probably, taking the Mass Pike out, that's about Newton right there, Newton mass. If we wanted to do the same thing with wind, we'd be on this purple line, and that is probably the 128 beltway around Boston. And the wind turbines are to be spaced several hundred feet apart, a couple hundred feet apart, and occupy the whole landscape. So everybody would be having a wind turbine in your backyard. If you wanted to do that with wood pellets or biomass, it's this green line, and that's out, way far out, and it's forest, so you'd have to regrow the trees every year to make enough power to power Boston. So that's not going to happen. If you did it with a nuclear power plant or a few small gas power plants, it would occupy a small area here, much smaller than the green dot, but that's all you would need. And you would not need a new infrastructure for cables that have to run under rivers, through golf courses, and into battery farms that are going to catch on fire, basically. So the bottom line on all this, as far as energy goes, is that solar and wind do not replace fossil fuels. They add to them. We're not giving up, in the world, we're definitely not giving up coal. And as long as we have solar and wind and don't have enough batteries, we're always going to use fossil fuels to back them up. Now let's talk nuclear. I'll try to quickly get through these. So the reactors that I've been working on all my life started with this one here. In submarines, I used to make reactors on submarines in a plant 50 miles from here. And these reactors were made on assembly lines, and they went out the back door, 10, 15 at a time, each on a railroad car to submarine construction sites. And these reactors could come on land right now and plug into any place you want, and a few of them power the city here, or Providence. But they're the old design. They're the reactor that still has all that waste that I showed you outside. So the nuclear reactors that are used to power submarines actually went on land and became our land reactors. They don't burn all their fuel. There's a lot of waste. Now for the submarines, we recycle the waste, melt it in acid, and put it in more reactors. But for the commercial power plants, we haven't done that. This one here is a Russian reactor. Russia uses nuclear reactors in its icebreaker fleet in the Arctic. And they put one here on a barge, and they can plug it in. They could send this to Puerto Rico, which has suffered terribly from storms and hurricanes, and plug it in and power Puerto Rico and get it back running. Instead, we're giving them a few solar panels here and there that don't last through the next hurricane. But Russia's using these and they're going to send them around the world. They're not as aggressive as China, though. I'll get to China in a minute. This is Bill Gates' reactor in Wyoming. It's called Natrium. He broke ground last year and still hasn't got a nuclear license because our regulators aren't smart enough to understand what he's doing, or his engineers are doing. So there's a lot of regulatory hurdles he needs to jump through, but he's got money. He can pay the regulators to go back to school. So he's building a reactor that can burn the waste that I told you about that's sitting outside. Really good. These other ones, they're all licensed. So obviously the submarine reactor is, the Russia one is. This one's not yet. This one by Kairos Power is licensed for US. NuScale is licensed. These are all licensed in Canada too. But the one I really, really like is the one that I started working on at Raytheon. I see a Raytheon guy in the back. I think he was there when I was working on this. It's called the thorium molten salt reactor. This reactor is very small. This is its size. It's not under any pressure. It operates at atmospheric pressure. Its fuel is a liquid, molten salt, with thorium, another element other than uranium in it. This reactor physically cannot melt down. It physically can't explode. It's not under pressure. It burns all its fuel. There's no waste, very little. Most of the waste is medical isotopes that we use in the hospitals. And it can't be used to make anything that's in a bomb. If you try to, you die just accessing the material. The interesting thing about this reactor is that we gave it to China in 2009. The Obama administration was kind of fallen apart due to the economy crashing, and there were a lot of bad investments back then in solar and wind that crashed after billions of dollars. Solyndra, if you remember. So they had to do something to kind of give a signal that we're really still concerned about the climate. So the Obama administration gave this to China and said, here, it's the perfectly safe reactor. You can walk away from it if anything happens, and nothing will happen except some salt on the ground, no plume of radioactivity. You guys take it and you build it. And they said, well, come on over and show us how. And we did. We sent our engineers from Oak Ridge, Tennessee over to show them how to build this. Because here is what we did. During the Manhattan Project, we built molten salt reactors to power aircraft. So this is a Convair aircraft. This was the engine that we put together to power this aircraft. This is the reactor right here, putting hot gases through and sucking in air here that's shoved out of the back at high speed. That's called a jet. The Russians did that right here, and they were more successful because the planes weren't big enough to really fly a reactor around carrying nuclear missiles, because that's what we would have done it for, is to have our nuclear arsenal in an airplane. That's not a good idea. They're targets. Submarines are a lot harder to find than airplanes. But the Russians did it here, and they got away with it because their airplane was about the same size as this one, but they didn't put enough shielding in the aircraft, lead, to protect the operators or the pilots. They rotated the pilots, which is a polite way of saying they killed them gradually with the radiation. Nowadays, we have jets that are big enough and put nuclear reactors in it, but it's still not the best idea in the world. The Army in the 60s and 70s built reactors that look like this. This one powered a complete city under the ice at the very top of Greenland in the Arctic Circle. And it's still, some of the stuff gets classified. This one's unclassified. Just say Camp Century. Early warning radar that's up there, kind of like the one that's on Cape Cod, is powered by a nuclear power station. Okay, so I think what I want to do now is just say, what can we do now? I'd like to conclude by saying, what do I think we would do if I were to advise the next administration? Well, first, I would caveat it by saying that climate change is natural, A small amount of it could be man-made, we don't know. Humans have flourished with twice the amount of carbon dioxide in the atmosphere and at higher temperatures. That was the Fertile Crescent slide I showed you, where the temperature stayed pretty constant and agriculture flourished in the Fertile Crescent. We are coming out of an ice age. The glaciers are still melting. The sea may rise by 2 feet. I'm kind of worried about that. Well, I think a lot of engineers know what to do and how to do it if you say solve the problem. But the politicians control all the money and the energy policy. So I say, especially to young people, there's one student here in the room in the back, run for Congress.
Yeah.
Be like China. Now, what do I mean, be like China? Well, if you're in the Chinese Congress, you have to have a master's degree in engineering or science. They don't care about lawyers. There are none in the Chinese Congress. They're lower level, they're considered servants for patents. China has a lot of patents. So run for Congress in this country, because the politicians need to be educated. So what do we do now? In the modern world, energy needs to be dense and always on. That's the density thing. The renewables will continue to be insignificant on a world scale, 2 or 3%. Coal and oil are twice as polluting as natural gas. Reduce CO emissions, so you go to natural gas if you want to do it. Reduce the CO emissions in half immediately, switch to natural gas. To eliminate all CO2 emissions, switch to nuclear. That's what China will do. It won't be tomorrow, but they're on their way. They're building 135 reactors, and they're putting them where the infrastructure already is, where the coal plants are.
Nuclear has killed less than 100 people ever. That's not what you're going to hear in the mainstream press.
Modern nuclear power can't melt down, can't explode, produces no harmful waste. You don't hear that in the press because nobody's looking at it. The Nuclear Regulatory Commission, which is our regulator, if they last through the next administration, they're all going back to school because they need to learn about these reactors. They have to stop thinking, oh, we have to not let 1 bit of radiation leak from a nuclear power plant. That's crazy. We get more nuclear radiation walking on a granite mountain than we would in a nuclear power plant. So if you want to live in a democracy, do all of these things above before China does. Think about it. So most of this presentation was done with inputs from the Energy Council of Rhode Island, which is a new organization we formed here with these members. And we ask you to give us questions. You know, I'll make the presentation here available to be on the internet eventually. It's being filmed. And when you see this slide, you can call up any of these people. We'd be happy to talk to you about what I just said in more detail if we need to. So take the questions now. Yeah, Frank.
Could you explain the manufacturing process for a small nuclear reactor compared to the manufacturing process of a 300-foot waste turbine?
Well, sure. The manufacturing process for anything has to involve quality control, obviously, no. And in the small nuclear reactors, because I worked on a manufacturing plant, we had one quality control engineer for every manufacturing engineer. So there was always a black hat, white hat thing going on to make sure there was no fudging of data. You ever do that? Failure to midterm. The cause of the failure was malfeasance. It was supposed to be operators not giving, fudging the data. Well, that isn't going to happen in a nuclear power plant. I mean, I don't really know if the company, Vernova, pinned it all on operators fudging data. It could have been manufacturing processes that were off. It might have been a convenient way just to make it all go away. We're going to fire some people. Quality control is the way it goes. Small modular reactors are made on assembly lines like car engines. That's what I did. I made it. Anybody else? Thank you.
Yeah, we say what you know. That was good. I said. And then for that.